What is the sum of terminating fractions? Before we answer this, let's break it apart so we know what we're even asking. So, in this case, what is exactly a terminating fraction? A terminating fraction is a fraction whose decimal expansion stops. So, for example, the fraction 1 divided by 2 terminates because 1 divided by 2 is 0.5, and then an infinite string of zeros, which we just write as 0.5. However, the fraction 1/3 is not a terminating fraction because its decimal expansion features an infinite string of 3's. So that is why when we're asking the sum of terminating fractions, you see the fraction 1, which clearly terminates, 2, not 3, which doesn't terminate, 4, 1 over 5, 1 over 6 also doesn't terminate, 1 over 7, 1 over 8, 1 over 8 would terminate, so we would put it in our sum. Now the question remains, though, how do we actually sum these terminating fractions? It might seem super daunting because we don't even really have a good grasp of terminating fractions other than this loose definition of it stops. So the first thing we'll do is try to formalize what does it mean for the decimal expansion to try to stop. Now, in order to do that, we got to consider decimal expansions. So, decimal expansion. The very first thing about decimal expansions that you'll notice is that they are A, expansions, and that they are B, decimal expansions. This decimal part is very important. If you know some metric units, you might know that deci is the prefix meaning 10. This means 10, the deci part specifically. And deci is going to be very important here. 10 is the key player. 10 is important because it's going to give us our grip on which fractions terminate. Because look at all of these fractions. Let's write out a few more. So we have the ones that I wrote down already. We have 1 over 1, plus 1 over 2, plus 1 over 4, plus 1 over 5. But let's try to write out some more. 1 over 6, that doesn't terminate. 1 over 7 definitely doesn't terminate. 1 over 8 does terminate. It's 0.125. 1 over 9 doesn't terminate. 1 over 10 terminates. And then 1 over 11 doesn't terminate. 12 doesn't terminate. 13 doesn't terminate. And the reason I'm going through these things, by the way, is because, for example, 1 over 3, it's prime. And because it doesn't go into 10, we could say just by long division is that 3 going into 10, you start with your 0 and 3, but then you subtract 3, so you go 3, 1, and you add your next 0 on, and then you get the same exact thing, and then you subtract your 9, and then you get 1, and you add your next 0 on, and then you get another 10, and then you get another 3. So the reason, fundamentally, that 3 doesn't terminate is because 3 doesn't go into 10. This is the first key insight. So I'll just write it down here. The reason 3, or any number really, wouldn't go into 10, or wouldn't terminate, I suppose, so 1 over 3, wouldn't terminate, is because it doesn't go into 10. So, well, rather it's that it doesn't go into 10. It doesn't go into 10. We're going to skip over this a little bit. Doesn't go into 10. And this is why 10 is so important. Being our base, in order to calculate a decimal expansion, we truly just do this long division. The long division is the method to find the decimal expansion, and the decimal expansion is key here when we're talking about terminating fractions. So, clearly if 3 doesn't go into 10, neither would 6, for example, because 6 is just 3 times 2. And nor would 9, which is just 3 times 3. And you might get where I'm going here. 12 won't, it's just 3 times 4. So, any multiple of 3, namely also 3 equals 3 times 1, won't go in, because 3 itself doesn't go in. Any multiple of 2, however, will. The reason any multiple of 2 would go in is because 2 clearly divides 10. It's one of its factors. So if you multiply this by 2, it's the same as the divisor just getting multiplied by 2 also, or the, who knows what it's called, the quotient, that's it. If you said 2 divided by 10, this is going to terminate, it's going to be 0.2. But if you said 4 divided by 10, it's just going to be multiplying this by 2, so 0.4. So what we have learned so far, or realized really, it's not so much learning, what we've realized so far is that the factors of 10 will be the only numbers that cleanly divide it, the only numbers that terminate. So the only numbers that terminate are, or really the only fractions that terminate, are the fractions involving only 2 and 5, because 10 equals 2 times 5. 2 and 5 are 10's factors, so anything else will have an infinite loop of not going into 10. So the numbers are 1 over, and then some combination of 2 and 5. What combination? Well, there are some interesting choices. The combination that makes the most sense is 1 divided by some power of 2, 2 to the a, times some power of 5, 5 to the power of b. Why would this make sense? Because you say, let's take a seed value. Our seed value is going to be 1. We're going to try to generate every single terminating fraction from 1. Well, really, every single denominator of a terminating fraction. Okay, well, we know that we can multiply by either 2 or 5, so on the right here we have we'll get 2 on the, that's the left. On the left we'll get 2, on the right we'll get 5. Okay, but from here we know if we were to just multiply by either 2 or 5, we would get a new terminating fraction, so we can either multiply by 2 again, get 4, or multiply by 5 and get 10. Here we'll also get 10 if we multiply by 2, but if we multiply by 5, we'll get 25. Now, from here, we can either multiply by 2 again or multiply by 5. So we get 8, or we get 20, or we get 20, or we get 50 if we multiply 10 by 5, or we get 50 if we get 25 times 2, or we get 125 if we multiply 25 by 5. So maybe this tree is starting to make some sense. We need any number of powers of 2 times any number of powers of 5. And no powers of 3, no powers of 7, no powers of 23, just powers of 2 and 5. This is the key point, because now that we have a form for terminating fractions, so it's this keys, we have a form for terminating fractions, namely just what we wrote down to the left. Now that we have this form for terminating fractions, we can do things with it. The key thing that we're going to do with it is sum over it, because if you remember, our goal is to find this sum of terminating fractions. So what we do next is to say every single terminating fraction has this form. Well, let's generate every terminating fraction and add them together, and then we'll maybe have to spend some time evaluating that sum, but we'll be done then. So what we say is we're going to sum these all up. How do you do that, though? You've got 2 variables. If I just wanted to sum up, say, let's pretend that b didn't exist. B was just equal to 2. So if b was equal to 2, I could sum this up easily, because then I'd be trying to sum up, this would imply that I would be trying to sum up 1 divided by 2 to some number times, well, 5 squared is just 5 squared. And the sum of this is just going to be the sum using sigma notation, and if you don't know sigma notation, it just is a lazy mathematician's way of summing a lot of things. So like if you wanted to sum 1, 2, 3, 4, all the way up to 174, there's no way you would actually write out that sum, so you just write sigma of some index starting at 1, ending at 174, and going just adding that index at every point. So in this case, we're going to start our index at 0 because we want to include 2 to the 0. Then we're going to go up not to any actual number, but infinity, because we're going to include every single possible terminating fraction where the power of 5 is 2. And then we're just going to say 1 divided by 2 to the power of our index, I, times 5 squared. This is good, it's an almost, but we're still only adding fractions where we have a 5 squared. We want to, in theory, add fractions with any power of 2, and where 5 could be 0, 5 to the power of 1, 5 to the power of 2, 5 to the power of 3. We want to add the fraction of 5 to the power of 3 million. So how are we going to do that? Well, we're getting kind of devious here with our math, but we can do a nested summation. What I mean by that is we'll take everything that we have here, so take this sum, put some big old parentheses around everything, and then go inside. We'll say inside of this sum, I will use yet another sum, where I'll begin a second index entirely, j equals 0. J will also go to infinity, and the sum every time will be 1 over 2 to the power of I and 5 to the power of j multiplied together. This is going to get us every terminating fraction, because on the inside you say, okay, for whatever value of I we are, go through every single possible value of the power of 5. So holding the power of 2 fixed, get every power of 5. And then you don't hold 2 fixed. You increment it by 1, and then you get all the powers of 5. You increment it another time, and then you get all the powers of 5 for that one. So at I is 0, this is going to generate, just to write it out, it's going to generate 1 over 2 to the 0 times, and then it's going to generate 5 to the 0 plus 1 over 2 to the 0 times 5 to the 1 plus 1 over 2 to the 0 times 5 squared plus 1 over 2 to the 0 times 5 cubed, and this is going to go on and on. And then this is just one sum, because our next sum is going to be the exact same except 2 to the 1 times 5 to the 0 plus 1 over 2 to the 1 times 5 to the 1 plus 1 over, and keeping 2 constant, 2 to the 1 times 5 to the 2 plus 1 over 2 to the 1 times 5 squared. And then we're going to repeat the entire process, but with 2 to the 2, and then 2 to the 3. And we're going to reach every single terminating fraction. So I'm going to do this. You can always go back in the video and rewind if you want to see it again, but I'm going to need some space here, because now we have a sum, mathematical formula that technically gives us the answer. We just have to figure out how to evaluate it. So the very first step is to say we have these two sums, and really when you have a sum of sums, you have to consider what you're summing in each term. So actually I'm going to go back to what I had before for a second. We could rewrite this. Notice here we have on this very first row many powers of 2. What if we said, alright, these powers of 2 are no longer existing in here because we factor it out. We factor out 1 over 2 to the 0. And here we factor out 1 over 2 to the 1. So then this goes away, this goes away, this goes away, and this goes away. When you have a term that depends only on the independent indices, and it does not depend, for example, on I and j at the same time, it's just a multiplication, you can actually pull out the sum. So what I'm saying is that this here, let me just copy it to make things simple. This is going to be equal to, if you took the sum of I starting at 0 to infinity of 1 over 2 to the power of I times the sum from j starting at 0 to infinity if you just took 1 over 5 to the j. And the reason that this is equivalent, and really you can think about having parentheses here around your sums, is because you're saying for each row of powers of 5, just multiply it by a power of 2. By the properties of multiplication and foiling out polynomials, really just any addition I suppose, by foiling you will still get every single terminating fraction. But now we can evaluate this, because what else do we know about summations in this form. One very specific thing we know, if I was to say, prompt you by rewriting it as the sum as I goes from 0 to infinity of 1 over 2 all to the power of I, times the sum from j goes from 0 to infinity of 1 over 5 all to the power of j, is that this looks suspiciously like a geometric series. Specifically, what I'm talking about is that this looks like the first one is just 1 over 1 plus 1 over 2 plus 1 over 4 plus 1 over 8 all the way on. And then this second one is just 1 over 1 plus 1 over 5 plus 1 over 25 plus 1 over 125, on and on and on. And we have a very specific method that can deal with sums of this form. These are called geometric series. Geometric series. And I believe I actually have a video that derives the formula for geometric series, infinite ones and finite ones. But here, I'll just give it to you. We're so near to the conclusion, we just want to get the excitement over with. So, right here, because we're multiplying by 1/2 at every point, this first part here is going to equal 1 divided by 1 minus the factor that we're multiplying by. So 1 divided by 1 minus 1/2. This right here is going to be the same, except the factor that we're multiplying is no longer 1/2, it is now 1/5. So we say 1 divided by 1 minus 1/5. And of course, we're multiplying these things together. So this then is going to equal, well, 1 divided by 1 minus 1/2 is just 1/2, so 1 divided by 1/2 times, and then 1 minus 1/5, that's 4/5, so 1 divided by 4/5. And of course, if we're dividing twice here, we say 1 over 1/2. This 2 is just going to come up to the top, so we get this is equal to 2 times, and then the 5 comes up to the top and the 4 stays down, so the 5 comes up and the 4 stays down, and then the 2 and the 4, they partially cancel out, so you're left with 5 divided by 2, not 4. 5 divided by 2. The answer to such a crazy question is 5 divided by 2, because we live in base 10. Now, I would encourage you, if you want to see how can I extend this notion of summing only terminating fractions to any base, and remember, the base was how we determined that we were only going to use the factors 5 and 2 to build our geometric series, how would you do so? Alright, thanks for watching. Hope you derived some sense of enjoyment from it.